So what are we doing today? So we are basically trying to understand Cassandra's data modeling. How does it compare to a general RDBMS, and what are the various constructs, elements that are supported in Cassandra, and we'll look at each of them in detail as to what each of them mean and how you actually want to manipulate or handle them actually inside Cassandra for storing information and then retrieving information too. Okay, so the contents basically today will be to understand what database model is. We just want to define what a model is, and then we sort of look at analogy between RDBMS and Cassandra data model, how they are different, what are the various constructs which are there in RDBMS, and how do they compare to something which is there in Cassandra, what is there, what is not there, and some of those details. And then we'll talk about individual database elements which Cassandra supports. So what exactly is a database model? What a database model is basically a logical structure of the database, and fundamentally determines a manner in which the data is stored, organized, and manipulated. Okay, so why is it important? A data model is basically something which caters and tries to fit the needs of the business or the company, right? So it's something which is actually unique, again very specific to the type of usage of the application or the company or business, because not all businesses actually function in the same way. So database model always should be driven by the business needs. Very important thing to be understood, because it's not just that we go and prepare a storage model just for the sake of it, because the mechanism in which you store the data actually depends on the specific business that it caters to, because a financial data model is quite different from a general application data model. So there are some level of domain specific restrictions that come in picture. So looking at trying to understand the analogy as to basically trying to see what are the various elements on the RDBMS side and what is actually Cassandra provide and how is it different in a sense, and try to relate so that we can understand it better and understand it easily, because some terms are a little different from the existing RDBMS world. So let's try and understand. So in the RDBMS world, so if you see the table in the screen, the left side elements are all the database elements of RDBMS system, and the right side ones are the Cassandra system. So in RDBMS we have something called a database server, where you have many instances that possibly are running, very similar to a cluster, where you have many nodes which are actually serving your data requests, read and write requests in Cassandra. Similarly, you have a database which is basically a group of your tables put together, and then on the Cassandra side it's actually called Keyspace, because naturally it's a multidimensional a sort of a key value pair at the base. It's a column oriented database, so it's called as a key space. The database is called as a key space here. Okay, then table, and then a same very analogous one is called a column family on the Cassandra side, because it's a column family, because it's a family of columns where a set of columns are grouped together to form a single column family. Okay, and each column family naturally is very much analogous to a table, so it has rows and columns, very similar to RDBMS tables. One big difference, if you see, the primary key doesn't exist in Cassandra. I mean, it's not that it doesn't exist, you can always define, but the mechanism is Cassandra actually inherently provides you a primary key for every data that you're storing, and it actually sorting also is done by default on your primary key for the data that you're storing in Cassandra column families. Okay, so that's the reason it's not actually shown here, but you can define if you want to when you're creating your table. Okay, indexes, only two types of indexes are supported, primary and secondary, and yeah, as much as possible secondary indexes are required whenever we have specialized queries and you don't want to use your actual row keys to actually retrieve, but you want to index on some other field in the table, then you want to use secondary indexes. Okay, stored procedures, functions, absolutely a no-no. Cassandra does not support anything like a stored procedure or functions. one special thing that you see is triggers. It shows a star. The star actually means it's an experimental feature which is got included in the newer versions of Cassandra, and it's not an pre-built or inherent supported feature as of now. Okay, exactly. So I'm just coming to that, Paddy. So star actually means it's an experimental feature which got introduced in the latest version of Cassandra. I think 2.0.5 or 2.06. It's not defined as a supported feature. It's more of an experimental feature. When people have evaluated Cassandra for using it in various different applications, people felt the purpose of a trigger would be very, very useful when it comes to the applications. I mean, we know, right, in the RDBMS world, we use triggers for alerting, some sort of alerting saying that, okay, particular action has happened or some important data is by mistake deleted, so you need to take some corrective action or things like that. So for those cases were actually found to be very, very important in most of the applications that we use today. So Cassandra also started supporting a feature of that type, more of as an experiment right now. It's not an inherent supported feature. Okay. Inbuilt functions, absolutely nothing. And on the data RDBMS side, we have SQL. On Cassandra, we have same thing, very similar, called Cassandra Query Language. And then no joins, no unions, no subqueries. Another very, very clear aspect which says no relational database specific stuff. So almost all of them are a purely denormalized based system. Okay, storage system. So sorting also is an experimental feature. It just got added into the latest versions of Cassandra, the 2.0 plus. And then grouping, no group by, no commit, no rollback, so no support for transactions absolutely in Cassandra, inbuilt. And then if you see one special thing, right, so there is something which is not there in RDBMS which is there in Cassandra, which is collections. Again, a very specific property which comes because of its inherent nature of Java. Because it's implemented in Java, so you could actually store your collection structures. So it supports basically lists, maps, and sets which you could use for storing your data directly into your database. A very, very useful feature, and we will see the value of it when we are actually going forward, running through some set of practicals, and when we do our modeling and etc. When we do our database modeling and etc., you will see how it is very, very important and how it really helps in storing useful information. So you could store a collection as is. The only difference is naturally the collection has to be, it's again a pretty similar, you can read and write, you can actually add, delete anything from these collections, very, very straightforward. Okay, partitions are any of the partitions because you are actually can partition data and store them as multiple, in the case of database we call them as multiple shards. Here we call this basically multiple partitions which actually go into multiple nodes in the cluster. Okay, so cluster. So one most important thing that you need to understand is Cassandra is naturally the cluster is the top level parent sort of thing for the entire Cassandra system, right? So cluster is a container of key spaces, very similar to a database server which has many instances, and each instance is responsible for a specific database or other set of databases. Very similar to that. A cluster is a container of key spaces. A key space is basically a database any day, right? It's very similar or analogous to a database in RDBMS world. And what is a cluster made up of? It's made up of nodes. Nodes are basically multiple instances of Cassandra running in the form of a cluster. So Cassandra sort of assigns nodes in the form of a ring. The reason being is, as I said, the Cassandra is actually a system which got developed by a lot of experiences that were gained from Dynamo, Amazon's Dynamo, and then the Bigtable clone, Bigtable from Google. So it's basically a mixture of these two. So one most important thing which you need to look at it is this one beautiful paper. I mean, I don't remember it right now, but it's actually something which I had read I think a few years back. And it was written by some Facebook folks and some other folks, where there were actually two people writing it. One of them was from Facebook and one of them from some other place. So it actually talks about the various experiences that Amazon Dynamo has gone through before actually reaching to a place where it is used in Cassandra. So they basically had gone through 7 different steps to reach the place where Cassandra is today. So first they started with a token ring model where we talked about a set of nodes where you use a token to get to take up the responsibility of sort of a leader election mechanisms, where you want to elect a leader in the set of nodes connected together, and then the leader sort of helps in coordinating most of the activities or checking things. And so there were several different models that were tied, and all of them are pretty much similar to the token ring style of networking model that is there in the general networking world. So that's probably the reason why actually Cassandra, it says that the nodes are arranged in a ring. So the ring concept came from there, and then it just it's very easy to understand that they are all connected in a way, and they're connected in the form of a ring. So each of them can talk to any other people. So there is a mesh network between them in a sense. So ring is something which you will see very often everywhere. That's probably the history behind this. That is basically because of the various different models that the gossip or the communication between the nodes actually came from. It's called, it's actually always termed to be arranged in the form of a ring. Okay. So and yeah, as we said, it's always it's a system which is designed with several machines operating together. Okay, it's specifically meant to be operating in clusters. Okay. So cluster, then let's get to key spaces. Okay, in Cassandra, Keyspace is very much similar to a database. So a cluster, as we said, is a container for key spaces. Now key spaces are basically used to group column families together. Okay, the purpose is basically simple, right? So I want something which are related information of a user or related set of column families or tables to put together so that I can actually easily sort of from the application perspective, I can say this group is something which I want to interact with, read and write from basically. So the key spaces are used to group column families together. Key space has a name and a set of attributes that define key space wide behavior. We'll look at what the attributes are. Okay. So generally a cluster, most often than not, in a typical deployment scenario, a cluster has one key space sort of per application. I mean, there are cases where you would use it, but we will talk about them a little more in detail. It has one, most often than not, in the general deployments, it will have one key space per application. So Cassandra has a set of key space as attributes, what we call it as a replication factor, replication placement strategy, and it's actually a group of column families, right? So what is a replication factor? A replication factor basically means what are the number of copies that you need to store in a cluster depending upon your needs, right? So which is basically what is the number of replicas that you need to store inside the cluster. Say I have basically a partition of data. Let's make life a little more simpler. So if I say I have say 1 to 100 keys to be stored, and I have say 10 nodes, so each node probably has say 10 keys, 1 to 10. I'm taking just an example. Don't think that it will actually store in this way, but yeah. So 1 to 10 is probably node 1, 10 to 20 is node 2. So you're partitioning the data. Okay. So now 1 to 10 is basically sort of allocated to node 1 as its responsibility. But there should be multiple other nodes in the cluster who should have this copy, because in case if node 1 goes down, there is somebody else who will actually service your request. So what is the number of copies that you store inside the cluster is what is called as a replication factor. So it's a key space attribute. So at the level of key space, you can define what is the number of replicas of the key space that you would actually store inside the cluster. The replication actually happens on your key basis, basically your row key basis. It's not really like it's an attribute which you provide at the key space level though. Okay. And what is a replication placement strategy? Replication placement strategy is how these replicas are actually placed in the cluster. The various nodes in the cluster, how are they placed? How do you choose your replicas? Who should be my replica for data 1 to 10, which nodes out of the other 9 nodes should be the replicas for my data in 1 to 10. So there is multiple different strategies that actually it uses internally to choose that replica. The purpose is to derive the highest benefit out of it. So the reason why 3 is used, right? So basically, if you look at it in most of these deployments, we are mostly talking about multi-data center deployments, because Cassandra, as we said, is built for running huge amount of data. It's basically to store, say, millions and millions of records all at one shot. So that's the reason why we always talk about multi-data center deployments. Now the reason for 3 basically is that basically in a data center you basically have racks, okay, the physical racks where you'll actually place your servers, and then beyond that you want to basically make sure that you maximize the availability. So how do you do? So you place your first node in one rack, and then the next replica, the first replica, basically your master is in one rod. Don't call it as master, let's not call it, it's just for the sake of understanding I'm calling it as master, because there is no master, no slave in any sense, just that there is a partition allocated to it. So it's like say 1 to 10 is allocated to node 1, so that is actually stored, is placed in say rack 1. Similarly, the next replica, the replica of 1 to 10 is always chosen in a different rack than the existing rack, so that you actually get the rack failure fault tolerance in a sense, right? Rack fault tolerance in a sense. So then again, when you have multi-data center deployments, you're always talking about if the data center going down. So then the second replica, when you're saying a replication factor of 3, we're talking about 3 replicas, right? So there is one copy, then there is a second copy which is in the second rack, and the third copy is actually placed in the other data centers, so that you have a data center failover capability. Similarly, if you have more number of data centers, then you will probably have a fourth copy also, which will be in the other data center. So you have 2 data center level failure capabilities. So it's arranged in such a way that you get the maximum benefit out of it, and that is what we call it as the replication placement strategy. And in a general sense, right, so there are 2 types of strategies which actually it uses internally, but now the latest version, it was always used to be a default one, a simple strategy. In case if you don't use any strategy while creating the Keyspace, it used to use it as simple strategy, but now it's changed, and now it automatically uses network topology strategy. Replication is basically the placement strategy actually tries to maximize the availability and fault tolerance of your of the replicas. So that's the main reason. So the default replication strategy is called as a was called as a simple. Rather, it's not default anymore. You can still use a simple replication strategy. Simple replication strategy says that basically what it does is you have basically several partitioners which actually help in partitioning the data inside Cassandra, and probably very similar with most of the other systems out there. So the partitioners sort of divide the data into multiple partitions, and then they will give one partition as an ownership to one of the nodes. Then the replicas of that partition will be written or will be stored in the other nodes. How does the additional replicas get stored? In the simple replication strategy, the next nodes in the clockwise fashion in the ring. Okay, so when we do when we install a cluster, we always talk about nodes arranged in the form of a ring. Okay, so the simple replication strategy says when I'm traveling in my ring in the clockwise fashion, whichever the node that I find immediately next to me will be used as my first replica, and then the subsequent node will actually be used as my second replica. So I'm always traveling in the clockwise direction. In this case, if you see the example out there in the screen, so we have basically 4 nodes, 4 node cluster of say Keyspace of let's not worry about what token values, we'll talk about it in detail. So it's basically the Keyspace is of 100 keys, and it's broken down into 4 pieces, 4 partitions basically, and then one partition is allocated to each node. So 0 to 25, 26 to 50, 51 to 75, and 76 to 100. Okay, so A1 basically is the ownership of the node 1 now, which is in 0 to 25 Keyspace. So A2, which is its replica, is stored on the next node, which is immediately next to it in the clockwise direction. Similarly, A3 is stored in the subsequent nodes in the clockwise direction. If you look at B1, B2, B3, C1, C2, C3, all of them work on the similar principles. Okay, so this is simple replication strategy. So how do you choose your node is basically traverse in the clockwise in the ring, and then whichever is found next in the ring, you use a strategy. Okay, so network topology strategy. So network topology strategy is used when we mostly deploy in multi-data centers environment. So single data center, it always uses simple, but I think today the concept is a little different. So because network topology strategy is the one which has the maximum amount of efficiency. So because of which it basically has a fail-back policy. In case if you end up using a single data center deployment, it will fall back to simple strategy and still follow the same clockwise deployment of the replicas. Okay, so that's the reason the default is a network topology strategy now. So whether you deploy multiple data centers or you actually deploy a single data center, it can comfortably fall back to simple strategy and we get it working. Okay. So as I said, the most common way is 2 or 3 replicas in each data center is probably the most common one that people use, just to make sure that you get all the failover stuff. So coming to network topology strategy, it's like this. So if you look at again a set of nodes put in the cluster. Now there are 4 nodes from data center 1 and 4 nodes from data center 2 who are actually forming a ring, or a Cassandra ring in a sense, right? So all the green ones are the DC1 nodes and the blue ones are the DC2 nodes. So now if you see your A1 is placed on DC1 and then A2 is also placed on DC1, but as A3 is actually placed in DC2. So this is a network topology strategy, is making sure that you have the data center failover capability actually addressed. Okay. Similarly, C1, C2, C3, D1, D2, D3, everything works on a similar lines. You always make sure that the 2 replicas are in one data center and the 3rd replica is always placed in the other data center, just to make sure that you have rack failover and data center failover capabilities. So now column family. So what is a column family? Column family is basically a logical division which sort of associates similar data. Okay. So you want to group all columns associated with something similar, or something you have some, it's not a relation in a sense, but there you're always talking about something which is similar, which you want to always retrieve as a set, or you want to work with it as a set of information that you always, as far as your application is concerned. So you can group those set of columns into a single column family. Okay, it's associating similar data. So example is users column family, cricketers column family, and some things like that. Something which is very similar. Okay. Okay, so let's just talk about it a little bit more. Okay. So how does it work? So it's basically, if you look at it, column families in Cassandra can be static and dynamic. What does static mean is basically when you are defining a column family, you can define all your columns as part of it. Very similar to the way we define our table, right? So when I define a table, I'll define all the columns, column names, the data types which are associated with those columns, what kind of data information will be stored inside those columns. So all those things are actually defined when you define the table structure itself. In the case of Cassandra, you have 2 types of column families. One is called the static column families, the other one is the dynamic column families. So static column families is very similar to the way we define our RDBMS tables. But when it comes to dynamic column families, it basically helps you to define a column family without really defining the columns itself. And you can add columns at runtime. Okay, so you can, it absolutely doesn't have, even in the case of static column family, basically, it's just a way to understand a column family. That basically when it's saying static is you are defining your columns predefined, but it doesn't mean that you cannot add. You can always add columns at runtime anytime. Hardly matters. So you can keep on adding more and more columns as and when you need for your application. Okay. Yes. Okay. Okay. We'll talk about it. We'll come back to this use case later. It's not important, right? Let's understand the column family in detail. Okay, so static column family and dynamic column family. The advantages of ability to arbitrary application supplied column names. So you can actually create a column family called dynamic column family where you just define only the table name, but you did not define any columns. And you can add the columns at runtime. You can define the type of data that is stored in each of those columns also at runtime. So everything can be changed, everything can be managed, but yeah, once you define, you don't want to change the data type, right? So basically, if I've said that a particular column will store string information, you can't just go and store. You can't just after using it for storing strings for some time and suddenly you can't go change it to integer. So that is something it gives you flexibility when you are defining or adding the column to define the appropriate data type that will be associated with that column, which means that if I'm defining it as a stringified data column, which means I can actually store strings into it. I surely don't want to change it at a later date. You can still change it any day, just before you start writing data into it. You can change string to integer, integer to something else, and then store data. But once you store the data, the other data gets invalidated. If you want to change it, if you change it, then it will your data will be lost. So it's probably not a good idea, but where we want to change the data type at a later date. Okay, but it's dynamic, so you can always change it directly from your application. So as I said, Cassandra column family is schema free, absolutely, because you can arbitrarily add columns and remove as and when you need, depending upon your application. Okay, and it has two attributes, what we call it as name and comparator. The column family has its own name, and what's a comparator? We'll come to that. Okay, so it has something called a name and a comparator, and the other thing is it actually has a concept of super column families. We'll talk about what super column family is. So before that, we will understand what a comparator is. So as I said, so column family has basically a name. It's the name of the column family, and then there's something called a comparator, which actually defines the type of the name. So the biggest difference which you come into the RDBMS world and this one is, so in the RDBMS, when you define your table name and your column names, all of them are strings, right? RDBMS does not support column names of different data types, but Cassandra actually supports column names of any type that you want. There are several different types of data types that it supports. So the column name can itself be a date, column name can be a number, column name can be a bytes column name can be a hash value by itself. So there are multiple different types that you can use for column names. So comparator is mostly associated with the data type of your column name. Okay. So yeah, I'll give you some more examples. That's not just for the sake of defining it. So when we learn more about columns, then things will be a lot more clear. Okay. I will come back to what is super column family and etc. when we are talking about the columns. Okay. So column is naturally the smallest increment of data in Cassandra. So there is nothing which is smaller than column, because columns are grouped together to form a column family. What does the column contain? It basically has three different things. One is a name, a value, and a timestamp. Very important. Try to understand this. Okay. So every column has a name, value, and timestamp. And all of them can be of their own different types of data types what it supports, except for timestamp. Timestamp is actually the timestamp at which the column got updated. So timestamp is basically the timestamp of the edit or the update for that particular column data. Okay. So why it is used? So it provides you some additional specialized facilities because of that. What we call it as expiring columns. So what is an expiring column? The advantage is basically, say, when you have written some data into a column, and after some time, say, I can give you a very nice example for you guys. So, okay, let's take a travel booking application again. Okay, so assume that I have about, say, 90 days of data. I allow people to book tickets in I mean, a year in advance in general, right? We actually, the booking sites provide you a 1 year in advance where you can actually start booking tickets for. Say basically, if I'm in September, but I can book tickets for December now itself. Okay. So when a person goes and actually books tickets for December on that particular date, you surely have to fix some price for that date, right? So the column name itself could be basically the date, for example, and the value could be the actual price on that date. Timestamp is naturally the time at which you got that information updated. But assume that you are talking about, say, as I said, I have prices from, say, January to December. Now I'm in September, so my price, which is in June, the June price is not needed anymore, right? So it's because it's in the past. I absolutely don't need that data anymore, except for I need it for some auditing purposes, etc. So as long as I need it for auditing purposes, which could probably be a month old data, probably not more than that. If I surely don't need 6 months or 8 months old rates to understand how my system actually did and anything along those lines. So that data can be deleted. So the expiring column basically says that I don't need this data, say after 4 months of its occurrence. So something like I don't need September's data when I'm in January 2015, I mean. So the expiring columns helps in automatic deletion of this data from the database. So you can always mark the expiring column and saying that, okay, see, I don't need this data after 4 months of its expiry, basically, which means it's already being used or the date has passed. So after 4 months, the database actually automatically deletes the data for you and you don't have to really worry about it. So that is expiring column. An expiring column actually is a property that comes because you have the timestamp that's available. So if the timestamp, updated timestamp is older than 4 months, just clean up the data. Simple enough to say, right? Then there's something again called counter columns, another very useful and interesting concept inside Cassandra. So counter columns are basically counters. So if you want to do some, okay, let's take an example just to understand. So assume that you are actually streaming a lot of logs into the database and you want to count on the number of errors that are they've seen in the logs, the number of say 200s or 400s, different response codes, right? So I want to count on the number of response codes which are 400s, number of 500s which are occurring in the log file. So all those things can be easily done by what we call it as a counter column. The counter column basically you can increment and decrement directly from outside. So if you have to do, say you have an integer column in RDBMS, if you have to increment it, what do? You basically retrieve the data, increment it and update it back. So you do 3 level of operations, right? 3 operations indirectly. But in the case of counter columns, you can do it in one single operation. So you can just say increment this particular column by 5 because you found, say, 5 400 errors and it will automatically increment for you. So these are specialized columns which are provided in Cassandra for different purposes naturally. Okay. So coming to super columns. So as we said, right, so we always talked about there is no relation in Cassandra, right? So but if you have a situation where you're saying, okay, there is a user data and there is something called his billing data or something like that. So something like his financial data. Now we want to make sure that you want to see both of them together. Ideally, since they are actually have their own attributes, you want to keep them separately into 2 different column families. But at the same time, I want to see all data in one place using, say, particularly the user ID. Now, how do you do that? Since there is no relation, there is no concept of foreign key, it's just not possible. So a mechanism that Cassandra provides you, what we call it as a super column family. Super column family means that one of these columns in the column family is a super column. What does it mean? The super column will actually store the hash. Hash is basically the key of the other table, you can say in a sense. Of all the other columns in that particular table, it actually stores the key of that one. Indirectly, in a way, it is deserialized into a small chunk and stored that chunk under a hash key in this particular column family. Make sense? Absolutely confusing? The super column family is basically a, a mechanism of combining multiple data together, multiple types of data together, so that it's easily accessible from a single key, in a sense, right? But the only biggest disadvantages of super column family is you cannot read and write to the other information in the other table just like that. You have to denormalize. First thing is you have to deserialize it into a structure, and then you manipulate, and then again serialize it and write it back. So it's in a way, it's basically it's almost like you're zipping all the information and putting into a single column into this column family, in a sense. So since it has a lot of overhead, super column families are very uncommon nowadays, and people don't use super column families in most of the modeling. Super column family has been more of an understanding concept right now, because there are multiple other ways in which we can get away from super column families. Okay, and they have a lot of overhead on the Cassandra system itself. So generally, people avoid using super column families now, but it's a concept which helps you to understand that you can actually avoid relationships in a different way. And once super column family is there, the data associated with the super column are actually again sorted by that particular hash key, which is being stored in that column, which automatically means that you cannot have any more secondary indexes in that particular column family. So Cassandra supports only 2 levels of indexes, primary and secondary. And then once the super column family exists, the secondary index is not supported anymore. A simple use case, if you see in here, say assume that you have something called a destination and international destination, domestic destination. Each of them have so you want it's indirectly creating a relationship. It's as simple as that. But the relationship is it's like you are taken out your relationships and denormalized everything into one single table. It's as simple as that. So it basically is a super column family called destination, which is showing here, which has two keys, 2 hash keys indirectly. One for international destination, one for domestic destination. Each of them have information about the appropriate destinations categories into grouped under one single destination column family. So leaving out super column families. Okay, what is the limitation? As we said, so subcolumns have to be deserialized before you read or write a single subcolumn in a super column family. Okay, so let me just do one thing. Maybe I'll go back to you. That's easier. Okay, so let me just do this. I'll show you that first, and then probably it's easier for you guys. So I think I copied something here, which probably gives you a better example of it. 1 second. Okay, I can talk about something. Okay, so this is like, okay, you can call it this one. Okay, this is like a super column family. So you have a user list. User list is basically like Kathy, Terry, etc., or to be a set of users, and each of them have their own properties again, which are again special properties which are sitting in a different table, different column family, very similar to the way it's shown at the bottom, right? So you have keys called A, B, and BB, which are basically another set of keys, but each of them actually have data from multiple column families in grouped together. So in the first case, Apple column family and bar column family are actually grouped together as 2 columns associated with key A. So the green ones inside there are actually the columns of this column family whose row key is A. So A is Apple and bar. Apple internally means it has several columns, and bar also means it has several columns inside. So it's basically grouping the column families together to create some important, in a way, a relationship. So if you look at it, it's a simple example of a super column family. So what you're talking about is have a column family which has keys, and it basically is grouping multiple column families. So this table will have A, Apple, and bar. So it has 2 columns. One is Apple, the other one is bar. Each column, Apple, actually represents again a group of another set of columns. Bar also represent another set of columns in a different column family. What is a key? So key basically is like is a way to access the information. It's like a row key, right? I have a primary key in my RDBMS table. I use that key to access information associated with all those set of columns for that particular primary key, right? So in a similar lines, row key is basically very similar to that. Key is here is a row key. So we have multiple column families, apple and bar, which are actually grouped under a single column family. But the way they are stored is they are not really stored as individual columns. They are all stored under a single column called apple and a single column called bar. Now whenever I have to do any manipulations on the subcolumns of apple or subcolumns of bar, I have to deserialize, obtain all the columns, modify it, and then serialize it and write it back to apple column. Similarly, I have to do the same thing for bar. So that is the biggest overhead with respect to a super column family. And that's the reason they have gone out of fashion and people are not being used, because it actually adds a lot of overhead on the internal of Cassandra itself. I mean the way operations and etc. Okay. In the case of super column family, absolutely right. It will be slow naturally because there's a overhead of deserialization and serialization. And again, depends on the number of super columns that you have in a column family, it will be more worse. It can become worse too. So they actually have got away from super column families by using composite keys. So the storage actually, when you have such kind of relationship brought in, they actually create a new column family which has the columns from either of the column family put together, which are useful to you. So always you create a new column family and never use a super column family as much as possible, so that makes your life easier and better when you are doing your data model. That's the concept. Okay. So coming back to data types. Okay. So every column, as we said, has multiple things, right? One is the name, the value, and then the timestamp. So the name can be of a different data type, value can be of a different data types, even the keys inside Cassandra, the row keys themselves can be of a different data type. So everything can be of any specific data types that it supports. So if you look at it, these are the set of data types which each of them support. So the name, the key, and the value of the column, all three can be of different data types in Cassandra. The various data types supported are ASCII, bytes, lexical UUID, which is again some sort of a hash, long, integer, UTF-8 for all stringified information, and timer UUID where you want to use timer-based hashes as the column names. So these are all the various data types it supports, which means that my column name can be of any of these types. And in case if you don't specify any types, the default type is bytes. It uses bytes as the default type. So the different data types that it supports are ASCII, bytes, lexical, UUID, long, integer, UTF. Fit and timer. So if in case you don't define any specific type, it uses bytes always. So now how does the data types actually work? So there is something called validators and comparators. So comparator, which I said, is the data type of the column name. So if you define your column name is of type say UTF-8, then it will make sure that all your store is in line with a general string. And if you don't store string and you try to store a hash, it will come saying that sorry, it's not allowed. Similarly, in the case of the column value, right? The column value is called a validator, and even a row key, either of them is called a validator, where it actually validates the data type of your row key or the column name, column value basically, sorry, column value or the row key. So in case if you say your column value is long, then it will make sure that the data that is stored is always long, and if you don't try to store anything else, it will say sorry, I don't understand what you're talking about and I cannot store it. Similarly, row key. So there are three different things, 2 validators and 1 comparators for every column family that you create, one for row key, one for column value, and one for column name. Okay. So you have to set the appropriate data types while storing the data, and you can change the data types also on the fly. So the moment you change the data types, so I mean naturally not a preferred option after you start writing the data to it, but in your definition you probably say you said it's an integer, but after you have created the column family, but you've decided that okay, I don't want to store integer, but I want to store string, I can always change it before you start writing the data. But once you have written the data, then preferably you should not change the data type. Okay, because other data will go for a toss. What we call it as wide rows and skinny rows. So wide rows basically means I have a huge number of columns but less number of rows. So I can keep on adding more columns instead of adding rows. I can keep on adding more rows instead of columns. So you have flexibility of both. So decide what is more suitable for you and use that. So wide rows are basically talking about more columns. Example cases again, travel booking, where I'll probably be using more of columns, because for the same hotel I want to add more price information for different dates. So I'll keep on adding more columns for the same hotel. In a similar way, I can actually say, okay, I want to add more hotels into the system. Then you can add more rows. It all depends on how you want to store the information and what is more suitable for your application. So you can choose a wide row or a skinny row. Some of it is actually will be very, very useful when you really operate with it and you do the real modeling. We'll do that in our fourth class, where we'll actually talk about next week, where we'll talk about, we'll take a real example of a travel booking site, and then we try to model it, and then you can see how the data can be rearranged using multiple different types of storage systems or storage styles. Okay, a similar concept as well as RDBMS, again a composite key. It consists of one or more primary key fields. So whenever you want to have, instead of a simple column key, okay, instead of having it as one single type, you can combine multiple keys together and create a composite key. The advantage is, it's very similar. I think some of these composite keys actually help you to get away from super column families and etc. So you can say, I group two keys together and put it as one single key. So the default one generally that is supported is using a colon. Colon is something which is you can use as here example. If you see login, location, surname, first name, and age. So you can combine multiple keys together and create a composite key for writing data or reading data from Cassandra in your table. Okay. Another very useful concept which you can say is what we call it as valueless columns. So when I'm defining a column, I can comfortably define it just, I don't even need to name the column. I mean, in the sense like I can actually just give, I can just give a column name and don't give any value for it. It's all supported. So I can add a column without any value for it. Just the name, say something like I call it as say dates. I'll just add dates to my travel booking application, but I'll not write any rate to that one because I have not decided on a rate. I can add the rate later. So that's another very useful dynamic columns that you can actually are allowed in Cassandra. So you can actually just define column name and don't bother to add any value. Value you can write it later. The columns can be added dynamically. The column names can be defined dynamically. The column values can also be written dynamically. So it gives a huge amount of flexibility. That's the reason we always call it as a schema-free data model. So there's no predefined schema, so you can keep on modifying as you require. And not that you won't, I mean absolutely not. You won't change the existing schema that is defined, but you can add more and modify if required. Okay. So if you see now, here is basically I have 3 windows. Okay, which is basically a cluster. I have a cluster of Cassandra instances running. So it has 3 instances running on the same box right now. This is a little bit a special mechanism that I use for Linux. I'm sure I think most of you guys might already know what we call it as virtual interfaces. So I create 3 virtual interfaces and sort of run 3 instances of Cassandra with those 3 virtual interfaces. And I'm running a cluster of 3 instances working together here. Okay, Windows generally doesn't provide an option, and I'm not aware of it. The only other option which I can think of running a cluster on a single box is probably by using virtual machines, say where you can run multiple VMs, either in a VM box or virtual box or anything of that software. So run multiple Linux VMs, and you can connect all those VMs together, or rather Windows VMs, doesn't matter. Connect all of them together as a cluster. Okay, make sense? Is that clear? So in my case, I'm running say 3 instances on virtual interfaces, which is more of a Linux or a Unix concept, but I'm not sure whether Windows, I'm not a Windows person, sorry for that, but I don't know if Windows networking provides you any sort of facility to run virtual interfaces actually on the operating system. I know that you can do it using VMbox, VirtualBox, but not virtual interface. Okay. So what I'll do basically is I'll start this is basically the deployment. So I'll show you the deployment environment. I'll actually show you the configuration information. Then we will run some simple practical examples before we close the session today. Okay, cool. So if you see, I'm actually this is my home directory. So Cassandra. So, okay, let me just show you what it is happening. Okay, so I have say multiple instances running. As I said, each of them are in their own folders here. So this is the zip file which I have downloaded, a binary zip file. So when you unzip the binary zip file, I get one of these folders. Okay, and in case if you guys can't are not able to see, or it's taking time to appear on the screen, please stop me. Then it will be easier for me to actually explain better. Okay, so every installation basically is one. So I've gone into Apache Cassandra. So here we have multiple different folders in every Cassandra distribution. Okay, this is a binary distribution which I'm talking about. So if you look at it, there are bin. So here there are multiple folders. There is something called conf. So inside conf, you have basically what we call it as Cassandra.yaml. So Cassandra.yaml is this one. So this is the Cassandra configuration file. So if you see, there is something called a cluster name. So a cluster name is a mechanism of grouping multiple nodes together into one single cluster. So all nodes which are part of the same cluster have to share the same cluster name. And this is a default cluster name called test cluster. So if you don't change anything, automatically all your nodes that you're running will actually be part of the test cluster. Okay. Then there is something called num tokens. We'll talk about this in more detail, but num tokens is basically talking about the multiple different partitions that you're supporting in the system. Okay, so then the initial system was actually using something called initial token instead of num tokens. So the new system, which is 2.0 plus, actually uses something called num token. So we'll talk about what is this virtual nodes, what are physical nodes, and all this stuff a little later. The physical nodes, or the physical partitioning concept, was used in something called the initial token. So the initial token basically is the hash which sort of represents the ownership of this cluster. So if I make my partitions into 4 pieces, it talks about which partition this particular node owns. That is defined by this parameter called initial token. We'll look at all the stuff, more details about how the initial token is set, what is num tokens, and all this stuff very detailedly in the subsequent classes. So let's not worry about it now. Okay. We'll talk about what is hinted handoff, maximum hint, and all this stuff in the next one. So authorizer and authenticators are actually basically the mechanisms of providing permissions, which you talked about, right? So you want to give a special key space specific permission to a specific user. You want to give write and read permissions on a specific a table and etc. So all those things can be done using your authorizers and authenticators. Okay. Okay, partitioner, I will talk about what is MoMA3 partitioner. So the most important things that we need to learn are these things. So if you see, there's something called a data file directory, a commit log directory, and there will be another important one called a saved caches directory. So these 3 things have to be absolutely changed if you want to run, say, multiple instances on the same node. The same physical machine. If you want to run multiple instances, you have to make sure that these 3 directories are different, because these are basically the actual data directories on the disk, so they need to be different for these instances which I'm running. So right now I have 3 different folders running 3 different instances, writing to their own local databases. Okay. And there is another important thing is called seed. Okay, let's not worry about what it is, because I'll tell you what is seed and what is bootstrapping and all this stuff a little later. So don't worry about it now. So this is basically the configuration files. I don't want to talk about in all of this stuff because we'll cover all this stuff in the subsequent classes where we'll talk about what is this listening port. So this is something called the listening port 7001. There's something called the listen address, basically the address at which this particular node is listening and talking. We'll talk about each of these settings in more detail. This is just a configuration file. Let's not really worry about it now. Okay, so get into the bin folder. So if you see here, you have multiple files. There is something which is a binary for Linux machine, and there's a batch file for Windows. Okay, similarly, this is the Cassandra server. So I have a Cassandra here, and there's a Cassandra.bat. So bat is for Windows server, and this is for Linux. So what I'll basically do is, I have actually started here. So let me just stop one of these instances to show you how do you run. So I'm stopping one of this, and then this is the way you run. You basically run this is a Linux mechanism, and you can actually run a batch file in the Windows. So I can just run a Cassandra-F, and then it will actually, -f means it's foreground. Basically, it's showing all your error messages and all the logs in the particular session itself. Okay. So the moment it says listening for thrift clients, it clearly says, okay, yeah, I'm ready to listen to the request. The default port on which the Cassandra listens to the client requests is 9160. For all application clients, they actually talk to the Cassandra host on 9160. Okay, so now I'll basically do a Cassandra CLI. So this is basically a thrift-based client which is provided for Cassandra, which uses a different style of interaction with Cassandra. But the CQL actually is again a different type of interaction. We'll talk about it. CQL is again something which inherently supported by Cassandra. This is a thrift-based system, and we'll talk about what thrift is and all the stuff in detail. So let's not really worry about it. It's basically a client for you to interact with Cassandra. Okay. So I'll just say Cassandra CLI. It says I'm connected to the test cluster. Okay, the version of the CLI. Naturally, CLI is duplicated and will be removed from Cassandra 3.0 onwards. So they have something called, after that there will be only CQL3 will be supported, not Cassandra anymore. Okay, but this is actually a very good system to learn, so that's the reason we will do it anyways. So if you look at it, show key spaces. I mean, anybody who's familiar with MySQL sort of might see some similarities in the way we do it, things here. Okay, so if you say show key spaces, it will actually dump a lot of information about all the internal existing key spaces. So let me create a key space, and then I will show you how does it work. Okay, create key space. What we call it as a Cassandra demo, and say about class 2 or something. Okay, I'm not giving any replication factor, nothing. I'm just creating a plain key space without any attributes. Okay, so it created a hash. This hash is basically a identity for this particular key space, which will be used for replication, etc. Let's not worry about how this and what cache it is. So let's go and see what is the key spaces now. So I'll go and see show key spaces. Okay, sorry. Okay, let me do this. It won't work. My Unix stuff won't work. Okay. Okay, so let me just browse to show key spaces. What is it showing here to me is okay. Okay. I have a lot of key spaces here. And again, I'm just locating. Okay, so this is what I did. Okay, so let's go back to the end somewhere and then see if I can find my key space, which I have created just now. Cassandra, my key space, road trips, system. Okay, where's my key space? Traces, World Cup, etc., etc. But where is mine? I don't see anything which is called Cassandra. Did anybody see it? There's another way to look at it. I'll show you how does it work. But yes, for now, I want to show you some options that it creates out of the box. So I wanted to do that. 1 second. Just hotels by city. Hotels. Demo 5. Demo 3. Demo 2. Demo 10. Actually, I ended up creating a lot of them. Demo 1. Demo control space. Yeah. Okay, so this is exactly what is the one which got created. So if you see, this is I did not give any information. So it automatically created something called replication strategy as network topology strategy, which is default. Let's not worry about what is durable rights. We'll talk about that in detail again. And then it said options is data center 1 and replication factor also as 1. So it has automatically made my data center as 1. I did not give any replication factor, so it didn't do anything as far as the replication factor is also concerned, and left it there. So if you go and look at the following Keyspace, right? So it clearly says something additional. So if you see, when I create a one with a replication factor as 1 and say a simple strategy, it automatically puts the options as replication factor as 1. So you can change this when you're creating the Keyspace and say, okay, my replication factor can be different. Okay, so now there is no column family right now because we just created the Keyspace. So that's the reason column family is empty. Whereas in the second case, you see there are column families. Okay, let's go ahead and create a column family. Okay, so first, for you to create a column family, inside that you need to say use, say Cassandra. What is that? Sorry, what did we do? Don't remember. Okay, I can do this, right? Cassandra demo class 2. Okay. Use Cassandra demo class 2. Okay, so now I have changed to the particular Keyspace. Okay, so I'm going to come inside and now I'll say create column family. Say again demo, say some demo 5 just for the sake of it. I'm not giving anything right now. Okay, just say column family and then say demo 5. Again, I did not give any attributes. Okay, so if I go back and say describe okay, so this is another way to see the information about your Keyspace. So you can see describe, very similar to again RDBMS to some extent. So right now what we did is we created a Keyspace called Cassandra demo class 2. Now I said to create a column family called demo 5, but I did not define anything, right? I just created a column name and a column family name and didn't do anything. What did it do? It basically put a lot of default attributes without really I'm telling anything. Okay, so as I said, the default key validation class is bytes type. A default validator is also of bytes type, and then the row key is also of bytes type. Since I did not give any data type, automatically it's put bytes type as a default. Let's not worry about what are all these parameters. We'll talk about all these things in detail when we are talking about Cassandra tuning, why we should have it, etc. And there's something called a compaction strategy. I think some people who actually have already gone through how to course might know what compaction is to some extent, and a similar kind of stuff actually holds good here. And then there's something called compression options, another very important. It has a default compression option for all the data that's stored, because we are talking about a huge amount of data being stored and manipulated at any time. Okay. Okay, so now coming back, let's run a few of the stuff. I'll take some of this copy so that I don't have to type all the stuff. I have several things here which I wanted to show. Okay, Okay, so what am I doing here is I'm calling something called demo sort of. Okay, let me just call it as demo only. Okay, may not work. Okay, let me just do one thing. Let me change this one properly, and then I'll create it. As a proper statement, and I'll call it as something. Okay, so let me call this as something called say Cassandra demo 2. I don't have anything like that, so I can just create this. Again, this is a replication. This is a duplicated syntax, but that's okay. Let's not worry about it right now. Okay, so I've come here. What I'm doing? Create a Cassandra demo 2. I'm saying my placement strategy is simple strategy. My strategy options is replication factor of :1. So you can give any replication factor you want here. Unexpected code somewhere where did I do something? Copy paste problems. Okay, this is code, that's the reason. Okay. Okay, so this is duplicated syntax, so let's not worry about it, but still, yes. So now it is created. So if I say use Cassandra demo 2, so it has changed it. Now if I just say describe Cassandra, I can actually do it without getting into the Keyspace too. So if you say this is what I've got created, so it's called simple strategy, and then you have a replication factor of 1. Fine. Okay, so then I'll go and create say column family. So here I'm doing is I'm creating a static column family. So this is exactly what I think one of them asked, Samket or someone, right? So how do you actually go and create a normal column family without a super column family? This exactly is a normal column family in a sense. Okay. So yeah, I mean this is some copy paste issue. So you give me a second, because I'll just make sure that it's the spaces are right. Typing takes a long time, so I keep all these things as reference because it's easier then. Because anything that's all these stuff are actually might take a long time to type. Okay, sorry. Okay, so what am I doing? I'm creating a column family called users with comparator type as UTF-8, which means it's a string names of the columns. Key validation class is also of UTF type, which is also a string. And then column metadata, which talks about all the different types of columns that I have. A full name, email, and then state, gender, and birth year. So there are 5 different types of columns that I'm creating. Okay, so now if you look at it, say again, if I say describe Cassandra demo 2, so it has now columns. You see that the columns are of the different types with validation classes, everything properly put in place. Okay, so now if you see my validation classes and everything else is also set. Since I did not give a column value validator, it still is by its type, but the rest of the data is already set. Okay, so now what I'll do is okay, so let me just show you how do I change that. Okay. So this is another way of actually changing your validators. So if I say this my validator was ASCII, right? So I'll say something, right? I'll change it as UTF-8. So everything will become UTF-8 now because I've changed to validator as UTF-8, right? It was already UTF-8, sorry. So why do change? It was already UTF-8. Okay, so now let's go back and add some data there. So you can change, basically if you want to, you can call it as, say you can change it as ASCII, for example. You just change it as ASCII so that you can see that immediately. Okay, so assume I can say like this, and then say, okay, ASCII, ASCII, you see now it will become ASCII instead. My validation selector becomes ASCII. Where is it? I created my table as users, okay. If I say UTF-8 type, it's not valid, so that's great. If I say ASCII, why is it not reflecting? It actually immediately it changes your data type to ASCII. Okay, let me check what's happening there. Okay, but it changes actually. Okay, so let's assume that we already have done. Okay, sorry. What's general problem? Unix problem. Okay, I always started typing as if it's a VI shell. Okay. Okay, so now we have created a column family called user with comparator and etc. Okay, so let me just try and insert some data there. So the way to insert data is something like this: set, if you say, okay, set users Bobby Joe email and bobjones@gmail.com. So I'm just setting this data. Okay, so how do you show the information? You say list users, it will show you the data. So this is the row key. So the row key here is Bobby Joe, column is email, column value is Bob Jones, and then there is a timestamp. So every column has name, value, and timestamp, as we talked about, right? And then row key is Bobby Joe. Okay. So similarly, if you want to do it, you can say get of say get users of say again Bobby Joe. Okay, and then you can say email, whatever the column you want. First row key, then the column, then the column family. If you say get, you will get the data. So you can retrieve using get, and you can write using set. Similarly, if I want to change say email to say bob@gmail.com, now you're basically indirectly updating, right? Now set, we just do a set and say get. So now it's at bob@gmail.com because you're updating in a way. So every set related to the specific same key, I'm doing an update. Okay, very similar. Okay, I can show you some more things, and the way delete is, you can say delete like this is okay. So delete is pretty much similar, called del users Bobby Joe. It's removed. So you say list, nothing is there. It's just a row key, but no data. Okay. No column list. How do we check using the SQL? We will work on SQL in a separate class. So I don't want to meddle it with right now. Okay, Ravindra, hope that's fine, right? Can I search using email? Absolutely yes. That depends on your indexes. So you need to create. So it's almost like a where clause, right? Select star something where email equal to something. So that's possible. All your where clause kind of queries are possible only if you have a secondary index created on that particular column. So without creating an index on that column, you cannot do. You cannot actually do a search by a specific column value. So for every column value that you want to do a search on, you have to create appropriate secondary indexes. So the mechanism, yeah, I can actually show you some more things, like you can do update. Okay, update actually means that I will throw away the new structure and basically create a completely new structure of the table. I just say go ahead and do this. So now I've okay, let me just take the space. Okay, some in the file missing. Yeah. Okay, so this is actually a problem. Okay. Okay, I can do it with comparator. I can type it. Okay. Okay, let me copy the rest. Problem was with the copy issue. Copy issues. Okay. Okay, so now if you look at the column family, nothing is there, just a key. So if you say describe Cassandra demo2, it basically has now an index called this one and just one single column family, one single column, because I've updated the entire schema structure itself. Right, so it became only one single metadata type with one single column and has an index called keys. So now if my birth year is a key as an index, so I can always insert information associated with the birth year, and then I can do a where clause on the particular birth year. So all those things are possible. Okay, and then similarly I can just delete and delete the entire stuff if I want to. Just say delete column family. What was the name that I gave? Users, right? Sorry, delete or drop. Sorry, it's drop. Drop column family users. Done. So no more column families. Now if you say list users, it will say sorry, it doesn't exist. Invalid request expression, etc. Because unconfigured column family user. Okay, similarly I can do a delete of the keyspace also. I'll say instead sorry, drop keyspace Cassandra underscore demo2. That's it, and no more. It automatically changes me to unknown, saying that my keyspace is deleted now. So if I say show keyspaces and or describe, it will say sorry, it doesn't exist. Describe Cassandra demo2, no keyspace, it wasn't found. Okay, so you can do a set, get, assume to change your data types, and then drop if you want to drop, and that's it. So these are the set of things that you can do using the Cassandra CLI based system, where it actually uses something called a thrift protocol behind the scenes. We'll talk about what thrift and all this stuff, and I will even show you how the thrift actually helps you to provide language specific bindings and all this stuff. Okay, do we get these queries in LMS? Yes, absolutely, Anubhav, and I will upload all the queries so that you can practice it. Yes, you will get it. Okay, can you demonstrate one composite column also? Yes, I think we will. Wait, I don't want to. Yeah, I mean creating that and etc. Showing it now, it will be a little longer. So I can actually show you in one of our examples. Again, very much related to the travel booking application itself. So when we run our class 4, that is next week session, we will have an example which will talk about composite keys and how it will be used to set up the data, and as well as I will show you even an example of storing collections also inside the database. Okay, so I think as far as yeah, so there is another way. I was talking about even the counter column families. So if you see, this is a way to create, but the only difference with counter column families is the columns of a counter column family, all of them are counter columns, which means it should have only counters and nothing else. That's a restriction that is there in Cassandra. So if I create a counter column family, all of them will be only counters, can be grouped together in that column family. It cannot have the normal columns and a counter column. So counter column family will have only counter columns, and the way to increment or decrement is using this way. Yeah, we will run some of these examples. Okay, let's not worry about it too much. Okay, I can always say do it. Let me do it anyways. What's the big deal? I can show you it right away. I had actually some other examples where I'll actually show that, but I can do this. Oh, but I have to create a Keyspace and everything again. I shouldn't have deleted the Keyspace. Okay, no problem. I'm going to create Keyspace. Okay, let me go back and create a Cassandra demo itself, and then I'll okay, 1 second. Then I can show you. Okay, so this is what it is. Yes. Okay, so then I have got the Keyspace created. So then say use Cassandra demo 2. Okay, so now I'll say create a column family. Page view counts. Again, same problem. Okay. Create column family. Let me just type it for everyone. Okay, column family. Let me call it as page. It doesn't matter what you call it as page view. And then just take this and say the default column type is counter column. Put this information in there. Okay, so there is a space issue still. Okay, so I have created a counter column family. Then I'll just say, okay, let me just show you what it has. Okay, if I say list page view, it will not have anything, absolutely nothing there, so 0 returns. So you can create the columns itself by running the first operation. So before you do any operation, nothing exists in a counter column family. If I just do this, okay, sorry, there is no page view concept. I called it as page view. Page view or page view, right? Okay, so let me change this. So now if you say list view, so there is a row key now with counter as so and so with value as 0. Now if I just say increment by 10, it will show you 10, value as 10. Got it? So that is the counter column families, but only counters can exist in a counter column families and nothing else. If I create a super column and decide to drop it, what I should be doing? It's just like dropping any other column, because super column is basically associated with the key that you store as the value in that particular column. So the name will be whatever the column you want to call it as, and just drop that column. That's it. So this is the counter column. So how does it work? I can even do a decrement and a similar lines called say it's called DCR. I said increment, and now I can say DCR, and then say it will actually decrement it, so it will become 0 again. So this is a way to work with counter column families, and as I said, the only limitation is, I think that will go away over a period, but right now the limitation is, I'm not sure if the latest versions have any limitation, but the limitation was counter column families are actually have only counter columns and nothing else.